how these can be used as good model systems to explore the BKT physics and quantum phase transitions. Well, we've already heard talks in the morning where we introduced the topic very nicely. So that reduces my job. But let me just thank the collaborators who have worked on this project. So the major work which I'll be presenting today is being done by Amar Varma, who's a PhD student in my group. Initial measurements were also done by Gorakhnath. The niobium nitride films were initially grown by John, and later, of course, Amar did most of the growth also, as well as the methods. So we got theory support from Ilaria, who was supported by Robert as a PhD student, and of course, Jack also helped with the simulations as well as the theory. Okay. So we've already known why 2D superconductors are interesting. We all want to look at emergent quantum phenomena. And here, since I'll be mainly concentrating on the BKT phase transitions and quantum phase transitions in this kind of systems, of course, we have seen many of these phase diagrams in the morning where we have gone from an ordered state to a disordered state through the quantum critical point. But now there are lots of work on disordered superconductors where they see the quantum Griffiths phase, which is a novel phase, and there you see this kind of a phase transition where you have an infinite randomness QPT. Most of these works over here have been done on many of these. Okay, so this is of course a very old field, and a lot of work has been done on conventional systems. You've heard about indium oxide, niobium nitride, titanium nitride, all these systems, and there are many experts over here who contributed immensely in the progress of this field. Of course, there are also a lot of work on granular films. Our group has also worked on them, aluminium, lead, niobium tin, and of course, Al2 here on granular films. But of late, you have a lot of work on novel disordered superconductors. We have novel geometries. Like here, you have a work on lead superconducting organic, inorganic hybrid superlattices. And here you can see that they see signatures of quantum Griffiths phase over here. You have, this is a report from Asholkov's group where you have experiments on nanodiamond hybrid arrays. And here too, you see the SID kind of a feature. There, of course, in the insulated phase, we see these gapped things where they can also probably speculate that they can see the Cooper insulator state. You have gated two-dimensional semiconductor superconductor arrays, where also you've seen this kind of a phase diagram. Then you have these this of two-dimensional materials. You have gate-tuned van der Waals superconductor, the ionic gated MOS2, where they also study the BKT phase transitions. So this slide is mainly telling you that you have lots of novel materials where this kind of physics is being studied. So what we wanted to do is we wanted to look at this kind of a system where you had superconducting films with periodic arrays of holes. And this kind of a system has, of course, been studied long back for a phenomena which is called as the vortex matching effect. So what is that? If you take this kind of a superconductor and you place it in a magnetic field where the magnetic field axis is parallel to the axis of these cylinders, then you start seeing these oscillations in the resistance. This is magnetoresistance with the magnetic field. And you start seeing these oscillations in a periodic way. And this periodicity is proportional to a flux quantum. So at the first matching field, you have one flux entering each of these holes. And this basically, the vortex lattice becomes commensurate with the underlying lattice or the antidot lattice which happens. So this kind of a phenomena, the vortex matching effect, has been studied a lot in the early 90s and early 2000s. We have also worked on these kind of systems where we showed that how you can tune disorder to be able to understand the mechanism of DND in these kind of systems. This is why I'm introducing, because we'll be using one of these as a probe to look at the QPTs in our system. Okay. So as I said that in these kind of systems, we want to look at BKT as well as QPT. Now why BKT? Because we have this system that it has been designed to have these holes, and these holes are nanoporous, and this will actually reduce the superfluid density. And if it reduces the superfluid density, we expect that the stiffness should also decrease. And if that decreases, then it should have a bearing on the BKT physics. And this is what was the main motive of being able to do this problem. And of course, when you can do this, you can also be able to tune disorder to get the SIT. And of course, the question which we wanted to ask is that whether we see this Bose insulator phase in these kind of disordered nanoporous films. Okay, so this has already been introduced by Professor Strong. So when you look at the BKT phase transition, the classic signature of a BKT phase transition is to look at the superfluid stiffness and the joint condensates at the transition temperature, which is the TIDES. And you identify this temperature where you have the vortex antivortex proliferate or unbind. And that's where you see the cut where this inverse 2T by pi cuts the superfluid stiffness. Now, conventionally, these BKT phase transitions have been studied mainly by transport measurements and where you use the Lenz and Halperin model to be able to find out the BKT phase transitions. Of course, you also look at resistance and then you can find out the BKT phase transitions. Very recently, you've also seen that noise measurements can also track the BKT phase transitions. This measurement, the measurement of the superfluid stiffness by the two-coil mutual inductance method, which was initially done in Lemberger's group at Ohio, is a very good measurement to find out the superfluid stiffness. And this is the measurement tool which we will be using in our lab to also look at the BKT physics in these kind of systems. Professor Strunk already showed this very nice measurement of being able to make these resonators and measure the kinetic inductance, where he showed these very nice sharp transitions of the BKT in the niobium nitride. Okay. So what is the challenge for probing the BKT physics? So the main requirement for observing a very clear and distinct BKT transition is that you should have a low superfluid stiffness. Now, how is it resolved? You grow either very disordered films or very thin superconducting films. But what happens in that aspect is that, okay. So this is a measurement on niobium films, which is around 2 nanometers. Here, of course, the superfluid stiffness has reduced drastically, but so has the TC. And with the TC, what happens? The TC also reduces. The inhomogeneity of the films increases. And of course, the BKT gets washed out. So inhomogeneity increases, leading to broadening of the transition, and you don't have very clear signatures of the BKT phase transition, and that becomes a problem. So we say that the ideal conditions to see the clear and distinct BKT transition is to have a low superfluid intensity or superfluid stiffness. You should have relatively high TC, low inhomogeneity. And this was actually shown, again, I refer to this work, which you saw in the niobium nitride films, where the inhomogeneity on the films were reduced by this atomic layer deposition technique. And this they observe very clear and distinct phase transitions at the temperature. So what did we do? We used a template-assisted synthesis, which is the analytic alumina template. This was used as a template. And this, of course, has periodic array of holes. And we went and deposited our niobium nitride films on top of these templates. So the film actually went and sat along the walls of these holes and formed these nanoporous films. So we actually did the measurements on 2 different kinds of templates. One which had a pore diameter of 40 nanometer with a pore period of 100 nanometer. The other one was a 20 nanometer pore and 40 nanometer pore period. Of course, when we grew the films, the first thing which we wanted to test whether we can see the vortex matching effect. So this we did by the dynamics shielding response using the 2-coil measurement. And here we replicate, so this is the real part of the mutual inductance as a function of magnetic field, and you can see these oscillations up to about 3 periods. You can, 2 periods, you can see it very nicely that the niobium nitride nanoporous films act as good pinning centers, and you can see the vortex matching effect. Now, to understand the level of disorder, we did the wall measurements and we got the KFL value of about 4 to 5. And of course, what we did is that for every template, we grew films with different thicknesses. So this was on 40 nanometer template, this is on 20 nanometer template, and we changed the thickness from around 15 nanometer to around 5 nanometer. As expected, the TC decreased as a function of thickness, and this is what you can see over here for both the templates, the TC decreased. Now, when we compare this with the niobium nitride non-nanoporous films or continuous films, we see that the TC is slightly decreased in case of our nanoporous films. But when we looked at the level of disorder, we can see that when we compare it with the, again, non-nanoporous films, you can see that it matches the KFL value very close to around 4.5, which we say that our films are basically mildly disordered. Now, effect of nanopores on the superfluid stiffness. As we already said, that the presence of nanopores should decrease the superfluid density and hence superfluid stiffness, and this is what we see over here. As you reduce the thickness for the 14 samples, you can see a decrease in the JS as you decrease the thickness, but also you see a decrease in the TC. Okay. Now, when we try to look at this 5 nanometer film, so we compare the continuous film as function of the nanoporous films. You can see that there is a huge drop in the JS. And this you can see for every thickness, this is what is happening. But the question which we wanted to raise is that whether this comparison is meaningful or not. Because here there is a huge difference in TC also. So this JS can be just attributed to the change in TC. So what we looked at, we started comparing films with comparable TCs. And there again, we saw changes in the superfluid stiffness. It was actually changing by almost 4 times. So when we plot the normalized plot, JS as when normalized with TC and T by TC, we see for all the, this is a 5 nanometer thick film. And you can see that as compared to the continuous films, the nanoporous films show a reduced superfluid stiffness. So therefore, to understand whether this is exactly coming because of the geometrical change of area. So if you just do a back of the envelope calculation, we can see that you take a 1 unit cell. This difference in the superfluid density should be around 1.5 times, but we see a much larger change in our films. So decrease in JS is much more expected, is more than the expected reduction in NS, and we thought that we should look at some simulations whether this can be explained. So simulations were done by Ilaria, Jack and Robert. So what they did is that they took a triangular lattice and they did it under the 2D dilute 2DXY model. And they simulated the nanopores by removing the sites. So you can see S is equal to 1, which is where the one of the sites have been removed. And W is actually the spacing between the nanopores. So what they see is that in their simulations also they see a decrease in JS for when compared to the clean case, and this is what the nanopores are giving. Now first we looked at the BKT phase transition through transport measurements, and here we can see that for a 5 nanometer film we can see this drop in. It's not very clear because you have inhomogeneity, you have broadening, and you can see this thing gets broadened. So we get signatures of the BKT phase transitions for the nanoporous films of 5 nanometer. We also see very small signatures for the 15 nanometer, which is quite thick film. So but of course, we took this with a pinch of salt because we know that we could have some heating effects in the transport measurements. And therefore, we looked at the one with 2 coil measurements. And here you can see that this is the measurement on the non-nanoporous films for a 5 nanometer film, and then for the 40 nanometer and the 20 nanometer. And you can see a good BKT transition in these kind of films. So is for the 10 nanometer films. So you can see sharp and distinct BKT transition. Now, Ilaria also went on to do some BKT normalization group flow equations, and then they sort of matched the temperature dependence of the superfluid stiffness with their calculations, and you can see that this blue line over here is our experimental one, and the green one is what they got from their theoretical thing. So you see that there is still some effect of probably broadening, and we see a small broadening of JS near TBKT. So what they did is that they incorporated the inhomogeneity in their calculations by a parameter epsilon, and which had a standard deviation of sigma. And that, when they used that, we could see that, okay, this is now, in the inset, if you can see that it reproduces our data quite well, with including the inhomogeneity in the films. So the refraction of the whole temperature dependence of the experimentally measured superfluid stiffness can be explained by this theoretical calculation. So this is for all the films. You can see a very good this, and you can see how this what its fluctuation regime is actually increasing as you go from the continuous films to the nanoporous films. So this was for a 5 nanometer film. This was somehow we were expecting, but when we started looking for a thicker film, so you can see these are the results from 15 nanometer. Here, the effect is not that drastic as like the 5 nanometer ones, but you can still see the PKT transition for the 15 nanometer. And this was something which was a surprise, which actually tells us that there is an effective enhancement of the 2D nature of the superconducting films when we go to these nanoporous films. And this is probably happening because you have these films where you have the films which are sitting only on the boundaries of these holes. And the films are, of course, the spacing is around 100 nanometer for a pore size of 40 nanometer. So it is much larger than both the thickness and psi, which is around 5 nanometer. So it makes them behave in the quasi-2D regime. So this was one part of the work. And then we wanted to see whether we can actually tune disorder in these kind of nanoporous films, so that, of course, we wanted to see the role of inhomogeneity, as well as we wanted, as I said, that we wanted to tune to be able to see the SI. So we took two different kinds of templates, so D1 and D2, and you can see when we deposited the natrium nitride on these two templates, the morphology of the films was quite different from these two films. So if you look at this one, which I call as low disorder, D1, here KFL is around 5, you see almost continuous films around the holes. But when we go to another template, which we call as the high disorder, here the KFL has gone down to around 1. See a very granular kind of an arrangement. So you get granular nanoporous superconducting films. And when we measure the resistance as a function of temperature, we see, of course, no surprises. Here, for the higher disorder film, you start seeing a broadening of the transition. So the TC decreases with increasing disorder, and the transition becomes much broader by increasing the disorder, which means that it is more inhomogeneous. So when we looked at the superfluid stiffness for both these films, this is a 6 nanometer result, and you can see that, of course, for the more disordered films, the superfluid stiffness decreased. So large reduction in the superfluid stiffness. When we looked at the role of inhomogeneity, what we saw that here I'm comparing two films of 5 nanometer and 3 nanometer for D1 and D2. What we see in the D1 films, which are the low disorder films, you can see the sharp transitions, which becomes much broader when you go to a more disordered one. So the advantage of going to the nanoporous films is sort of getting this by increasing the inhomogeneity. So the take-home message which we said that, okay, if you want to reduce the superfluid stiffness, want to see distinct, clear signatures of the PKT transition, you need to go to nanoporous films. But in the nanoporous films, if you start increasing the disorder so that the inhomogeneity increases, then again, you will start getting these broad transitions. So it adversely influences the sharpness. However, one thing which we need to note that if you look at the superfluid stiffness for the films grown on the D2 or the second disorder films, the JS becomes comparable to the DC, which means that phase fluctuations have started to dominate in these kind of films, and this becomes a good candidate to look at whether we can see this Cooper-paired insulator state in these kind of films. So this I will skip. I will just show this part. So this is the result which we wanted to show, that we made films of different thicknesses, both on D1 and D2. And we see that if you just compare the 6 nanometer films, you can see a clear superconducting transition. For the D2 film, you start seeing this plateauing of the resistance at low temperature. For the 4 nanometer, when we compare T1 and T2, this is plateauing and this has gone okay. Whether it's insulating, but you still see a plateau. For still lower thin films, like 3 nanometer or so, we can see this insulating phase, which goes for the D2 films. Okay. So what we did is that we looked at the vortex matching effect in this superconductor insulator crossover regime. So in the superconducting films, the 6 nanometer films which are grown on the D1 films, we can see these oscillations and we can see this strong VME with 4 matching periods. We also see it in the metallic regime, which is of course, here the resistance is not completely zero, but here also you can see the VMEs. Now if you look at the 3 nanometer films, we can see that both in the, so when you had you've grown films on the 3 nanometer D1, in the insulating side, we see these vortex matching effects. So which shows that you have the localized pairs which survive deep in the insulating regime. However, in the 3 nanometer D2 films, of course, we see those signatures of the 3 nanometer, which means that this here, the destruction is, it's not in the Cooper insulating regime. So this is the take-home message. In homogeneous nanoporous films, SIT governed by fermionic mechanism, and in granular nanoporous films, SIT is governed by the bosonic mechanism. But summarize, so I showed you the results on nanoporous films, where we showed that by making the films nanoporous, we are being able to reduce the superfluid stiffness, so such that we can see sharp, distinct phase, the BKT transition, quite sharp and distinct. And we see a good matching with the experimental results with theoretical simulations. And we see that this also enhances the 2D nature of the films. We also saw that in homogeneous nanoporous films, SIT is governed mainly by the fermionic mechanism, while in granular ones, you can see signatures of the bosonic mechanism, which enhance the pair. Thank you.
Questions? Okay, let's talk. I have one question. Why you think you believe if you want to study BKT conditions, the carrier density should be low. JC should be low.
The superfluid stiffness, right? So because we are reducing the geometrical area of our films, we think that the superfluid density will go down. And, that would have a bearing on the superfluid stiffness. Okay. That was our understanding, and that's what actually came out of the simulations also.
Yeah. So the nanopattern modulation, the major role should be just induce some more fluctuation, dissipation disorder, and makes the phase coherent harder to realize. So the transition regime should be larger. Then it's easy to compare BCS transition and BKT transition with a large region. But yeah, it's I think it's mainly for some dissipation or like that, fluctuation, phase modulation.
Yeah, because we also have these nanopores which are acting as spinning centers. So that would also give rise to whatever. I mean, can have these trapping of the vortices. Also, we thought one of the reasons of increasing, of course, as we said, to increase the fluctuations, right? So.
Okay. So for the last part, why in homogeneous nanoporous fields, SIT governed by fermionic mechanism, but for granular such fields governed by bosonic mechanism. Do you have any explanation or?
No. So what we can think is that, of course, as the microstructure, you can see that they are more granular. So probably the phase fluctuations is increasing over there, and you have pockets where you have where you can localize the Cooper pairs, and probably that's one of the reasons, but we don't understand it completely.
Okay, is it possible this from the sample quality or measurement resolution? Since our previous work for nanopatterns of YBCL fields, actually it's crystalline. It's not a granular one. We observed the beautiful quantum oscillations for 2E insulating state, both insulating state and superconducting state. And before our work, actually, Bronx University.
I had that result here.
Studied James. Studied amorphous Christmas field. It's also not a
and the data was there, which I skipped quickly here.
So not very consistent with this. Okay, so final comment for the beginning of the talk. Okay, final comment. For the beginning of the talk, you introduced many phase diagrams. Actually, this is a phase diagram from our two review papers and one science paper. Reference should it's better to put references there. Okay, thank you.
I've read it.
Yes, please.
So I have a very basic question because there is something that is misleading for me. So in the Baker condition, this is on the dissociate for some reason, because anti-vortex they can fit any position in the whole sample. So you have right sample to the ratio is the side of the score. But here the vortex, the anti-vortex, it will sit on your walls. So on the entropy point of view, you have much less entropy in the problem because you reduce the possibility and you force them to go into the level. So why should the BKT still hold in this case?
In fact, that was the motivation. We had thought that it would be completely washed out. In fact, that is what we had thought. We got something that was completely different. But I'm thankful for you. We started, it would completely washed out because we thought that it would just get trapped there.
So I was wondering if you knew of or if you measured the thickness variation of the films. What was that whoever decides an influence or not.
So thickness, of course, because we're going to very low thicknesses, we need to look at the thickness homogeneity over the film. So we do it at different places and we try to see that it is plus minus within.
Okay, so it's
in thickness.
Okay, thank you very much.